So your thought primer homework problems are not going to be asking you to compare pairs of simple sentences. Instead, you're going to be comparing sets of complex statements, 3, 4, 5, 6 statements. And the reason I'm structuring your thought primer homework that way is that I want you to be able to use indirect truth tables to evaluate statements in order to be able to evaluate a stated belief system, so that when somebody comes to you and says, here's what I believe about human nature, here's what I believe about fairness in sports, you can quickly and effectively evaluate that belief system by taking all of the statements that comprise the belief system and using an indirect truth table to see if it's possible that all those statements could be true at the same time. Because if it's not possible, then their belief system doesn't make any sense. And that could be really useful for us to know if we're being asked to respond to that belief system, or we're being asked to express our own belief system. So the problems in your homework, thought primer homework, are going to look more like this. We've got 4 statements, and some of them are fairly complex statements. Okay. Now, this particular set of 4 statements has a challenge that's kind of embedded in it that you're going to be contending with some of your other homework problems, and I want to go over here how to best contend with that challenge when you face it. All right, so to test these statements for consistency, we mark them all out on a single line, separating each statement from all of the others with a single slash, and then we assume that all of the main operators are true. Once we've got the main operators marked as true, we simply go about the business of deducing all of the logically necessary truth values of the component parts of these statements, okay? Now take a look at the operators here. This is where we encounter the challenge. The main operator for the first statement is triple bar, and all of the other statements have as their main operator horseshoe. The challenge that we're faced with is this. We're working from the assumption that all of these operators are true, but all of these operators can be true in multiple ways. That means that there is no logically necessary truth value I can deduce just by assuming the truth values of the main operator, okay? And this is going to be the situation you find yourself in anytime one of the statements in your statement set is not a conjunction, is not a dot statement, okay? A dot statement is true in only one way, and that's when both sides of it are true. So if you have a dot statement in your statement set, that's the place you want to begin. If you have as one of your statements a single letter with a tilde next to it, that means you're going to assume the tilde is true, and you can then deduce the truth value of the statement that it's next to, and you might be able to start your logical deductions that way. But when you're faced with a situation like this one, where you have all of your main operators true in multiple ways, you're going to have to create multiple lines for your truth table. And typically what you're going to want to do is you're going to want to choose the operator that can be made true in the fewest number of ways. So here, that's triple bar. Triple bar can be made true in 2 ways. It's true anytime both sides of the triple bar have the same truth value. And your horseshoe can be made true in 3 different ways. So we might think that going with the triple bar here is the way to go, since it's true with fewer true-false combinations. But we got this funky wedge statement over here on the left-hand side, and wedges can be made true in 3 different ways. So I could assume that E is false and the wedge is false, and that would allow me to deduce that N is false and C is false. But if I'm not able to successfully do all the deductions, I'm right back to square one, and I'm going to have to pick up one of these simple horseshoe statements and work with it. So I'm just going to go ahead and start with one of these horseshoe statements, okay? One of these simple horseshoe statements. There's 3 ways it can be made true, and what I'm going to do is I'm just going to start working through true-false combinations for this horseshoe statement right here to see if I can deduce all of the logically necessary truth values for the remainder of the statement with no contradiction. It only takes 1 time to do that. So if I'm able to do that successfully on line 1, I don't care about lines 2 and 3. I'm just trying to show that it's possible for these statements to all be true at the same time, okay? But if I'm not able to complete line number 1 successfully, I'm going to then have to go to a different pair of true-false combinations for the statements on line 2 and try those out, okay? So I'm just going to work from the assumption that H is true and E is true, okay? And so if H is true there, H is going to be true over here, and it's going to be true over here. And if E is true here, then E would be true there. Okay. Now what I'm going to do is I'm going to look for any further logically necessary truth values I can deduce based on the additions to the truth table. And I can't, okay? Because with H assumed to be true, C could be either true or false. C over here could be either true or false. And this could be either true or false. So there's no further deductions I can make. So what I'm going to have to do is I'm going to have to go to line 2. And I'm going to have to operate from a different set of assumptions about H and E. So I started by assuming they're both true. Let's try it when they're both false. Okay, so if H is false here, H is false there, H is false there. If E is false there, it's false there. I know that this C has to be false when H is false. That's the only way to make sure that this horseshoe stays true. I could mark this C over here as false too, but for some reason I've chosen to go to this C. Okay, so if C is false here, C is false there. If C is false there, that wedge is false. And if this wedge is false, this tilde is going to be true. Okay, but I don't know the truth value of N here. Could be true, could be false, because the right side of this horseshoe is true. Okay, but now let's look over here. We've determined that E is false. Well, in order for the triple bar to remain true when E is false, this wedge statement over here has to be false. And there's only one way for that wedge statement to be false, and that's when both N and C are false. And if N is false here, N's going to be false there. And look at that. We just proved that these statements are consistent, okay? So the theme here is this. Work slowly, work methodically, exhaust your options. You're only looking to prove that the statement is consistent or inconsistent. And you can prove it consistent by just showing one possible combination of true-false values with no contradiction where all of the statements are true at the same time. So we don't even need to do anything with line 3 because we proved on line 2 that these statements are consistent.